evening, everyone. Welcome to the week 5 problem solving session of the course Control and Tuning Methods in Switch Mode Power Converters. And week 5 is about modeling and analysis techniques in switch mode power converters. I am Teja Golla, a fifth year research scholar working under Dr. Santana Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me quickly share my screen. I hope you can see my screen.
Yes.
Okay. So in this 5, it's all about analysis. So this will be like a building block for the upcoming weeks. So in this week, we'll be learning about how to get the small signal model of any converter, but I'll be discussing about buck converter and Kelvin will be discussing about boost converter. So the methodology remains same, only the converter changes. So the model will slightly deviate, but the overall objective is the same. We need to get the small signal model. So there are different ways of getting the small signal model. Sir has taught, I think, 3 methods: state space, average switch model, and state space averaging. So I will be discussing circuit averaging and state space, not sorry, circuit averaging and average switch model, because they from just a minute, let me. Yeah. So you can also do state space analysis, but if you have like a freedom, then I would personally prefer circuit averaging or average switch model, because in this case we can see the circuit, whereas in the state space we'll only see the matrices, so you'll not get the feel of what is actually happening in the circuit. Whereas if you choose any one of these methods, then you can see this here we have a resistor, here we have an inductor, so this resistor is getting added, so that's why we are getting this. So you can actually see the duty ratio dependent terms, input voltage dependent terms, and other parasitics, and how they are affecting the model. You can also do state space averaging, but there it's more of mathematics. So you can get A, B, C, D matrices, but you will not actually know what is happening. But nevertheless, all the 3 methods are used to do small signal modeling. So all these methods are like they have their own pros and cons. In circuit averaging, you need to solve the circuit with all the terms, whereas in the state space, it becomes easy in terms of computation, because everything is in terms of matrix. So you can use MATLAB or something, and you can plug in the matrices to get the expressions. But as a from a circuit point of view, it would be better if we can understand the circuit and see the circuit, look at the circuit and how things are getting affected. So that's why I'll be teaching these 2 methods. But if you have any doubts in the state space averaging, you can also ask that, so we can cover that. But considering the time and whatever I have planned to discuss today, I have selected these 2 topics for today. So now I think you will all be comfortable with the buck converter diagram. So let me start with the first. I think we can start with non-ideal, because let us not deal with ideal and then go to non-ideal. We have R. So I am neglecting only yes, sir, so that it will, or maybe we can consider also the innovation. So this is real. Both the resistances I'm considering as R on, S bar, RL, L, RC, C, R, plus minus, we know. So in the case of circuit averaging, what we'll be doing is, so the first method is circuit averaging. So we'll have to get the dynamics. So the entire circuit will be using a transformer model, and then we'll make it into an AC equivalent, or you can say AC plus DC equivalent, or a small signal model. So we'll first deal with the dynamics. So let us start with inductor dynamics, and then capacitor dynamics. So I will start with the inductor dynamics. So when Q is 1, what is the VL? And when Q is 0, what is VL? Anyone? When Q is 1, what is VL?
V naught minus Vn. Sorry, Vn minus V naught.
Okay, but also we have now two more resistors. So V in minus V naught. But because it is non-ideal, we also have R on plus RL in series. So we have R on plus RL into IL, right? Two
Yes.
resistors, this resistor and this resistor. Similarly, for Q equals to 0, we will not have V in term. So minus V0 minus the lower side R on. So now we'll get this R on and this RL. So minus R on plus RL into IL. So sir has considered this as R equivalent. So I can also write, instead of writing two resistors, we can write it as R equivalent. So now combining these two, I can write VL in terms of Q, which is DIL by dt is equals to Q into V in minus V0, because it is Q dependent, others are always there. So there are no Q terms. So when we say circuit averaging, basically we are considering a average sense. So we'll not be considering the ripple. We are neglecting the ripple and we are considering in average sense. So now, like there is a term that is used to denote the average term, which is this. So whenever we use this term or a switching time period, this is a like an average. So when we are saying that it is considered in average sense, now we'll replace this L into d by dt of IL average over one cycle. Similarly, Q is there, so let Q be there. So I can write it as dV in, right? Q. So now average of QV in, what will it become? It will become dV in, right? Because it's an average of V in over a cycle of Ts. So Q is there for dTs time and Q is 0 for 1 minus dTs time. So we'll get dV in minus average of V0 Ts minus R equivalent into average of IL Ts over a period of Ts. So is this clear how we are getting?
Yes.
So now when we have approximated the ripple, then what is happening is we'll get a constant value, right? So we have studied that IL has a constant value. So we have IL Ts, we have V naught Ts, we have, yes, only two terms are there. So now this will become IL, this will become V naught. But whenever we are talking about an AC equivalent model, we talk about perturbation around an equilibrium point. So around steady state. So this IL and V naught, capital IL and capital V naught are steady state. But in order to get AC equivalent model, we'll give perturbations. So these are the perturbations, IL perturb and V naught perturb. And one thing is the perturbations that we are giving. So it is like a, you can consider as a slow sinusoid, which sir has explained. And the frequency of this perturbations are much slower than the switching frequency. So they are actually not affecting the uh, working of the converter. So basically what has happened is this is operating at a switching frequency Ts. So now we have considered the average dynamics over the cycle Ts. So the ripple is gone and we have considered the average values. But for AC equivalent model, we need to excite it with some perturbation, say sine perturbation. So sine has a frequency, so that frequency has to be much lesser than the frequency of operation of this, so that it will not affect it. So it is in a very slow sense, so that it will not affect the converter. Also, we are filtering the ripple so that ripple does not come into our calculation. So that's why ripple is gone. And the second aspect is the frequency is much slower. So now we need to replace these terms with these terms. And also duty ratio is there. So duty ratio also has d per term. So we'll consider d as, so average sense you can consider average duty ratio is it has a fixed duty ratio. Also it has d naught, d per term. So is this clear? Okay, if you have any questions, you can ask. So now I will write the expression L into d by dt of IL will become 0. So we have IL per term is equals to V in also we have to consider, right? I forgot to write V in. So there is V in. So this is like average D into average V in, because V in also can vary. So we need to consider V in as well. So V in is equals to V in plus V in per term. Okay. So now let us put all the terms. So we have d plus d per term into v in plus v in per term minus v naught plus v naught per term minus r equivalent into il plus il per term. Okay. So now we have LDIL per term by dt. So let us keep it on the left hand side itself. So L into DIL per term by dt is equals to, so now I write dv in minus v0, so I'm segregating, plus d into v in per term plus d per term into v in, or let me write in this way. So we have dv in first term and then here v naught per term. So now we have d per term right. So we have d into v in plus v in per term plus d per term v in plus d per term v in per term minus v0 plus v0 per term minus r equivalent into im plus im per term. So we ignore the second order dynamics. So perturbation is small. So we are multiplying basically two small terms. So we have to ignore this. So like these are some approximations that we consider in the process. So this is the final expression that we are getting. So is this clear for everyone how we got this expression?
Yes, it's clear.
So now what we'll do is we'll represent this in terms of a circuit. So first we have an inductor. So we'll write an inductor. Okay. And we have a resistance in series. And then we also have an output, right? Here we have an output. And here we have some voltage. Okay. So now let us write one by one. So this is input term. So D into V in plus V in per term. And this is L and this is R equivalent. And the current that is flowing through this is IL plus IL tilde. So you can ask then it should be d by dt of IL plus IL tilde. So d by dt of IL is 0. So that's why this term has vanished here. But this also has d by dt of IL plus IL tilde. But IL is constant. So that's why the derivative is 0. So we are getting this term. So now we have completed this term. We have completed this term and output term is been remaining and this term is remaining. So this is an voltage source. So we have to also add this voltage source. It's a dependent. So minus plus and then so this is our d part of v and this is my plus minus v naught plus v naught tilde. So these are the inductor dynamics. So now the advantage of this method is I can see that inductor is there, equivalent resistance is there, and here we have some dV in related term and output related term. But if you see, we are getting some additional term because of the perturbation, d perturb. So we can actually visualize the circuit and see, okay, what is happening here. Compared to this circuit, we can say that this entire thing is replaced by some voltage source, and now output is replaced by this. And because we have only dealt with inductor, so RL plus R1 has become R equivalent, and then we have some additional terms. So we can actually visualize what is happening in the circuit. In the case of state space, it is not there, so that is not something that I prefer. So that's why I'm showing this method. So now inductor dynamics is over. Now let us go to capacitor dynamics. So the method I have went in detail. So now we can go a little bit faster now that you have understood the process. So capacitor dynamics, you know that IC is equals to C into dVC by dt, right? So we'll have which is IL minus I naught, right? Which is IL minus V naught by R. So I have basically neglected RC, but I'll add it there. So if we consider RC, it will make our life simply little bit difficult. So I have ignored RC, but we can add it towards the end. So now the same thing we'll do C into d by dt of V naught plus V naught tilde is equals to IL plus IL tilde minus V naught plus V naught tilde by R. So if you see, IL plus IL tilde is already coming from here. So now from this we need to subtract this, and V naught plus V naught tilde is also there. So basically we need to add a resistance here, and then this is the current that is going through the capacitor, and capacitor is C d by dt of the voltage across it, which is V naught plus V naught tilde. So now it becomes very simple. So basically what is happening here is we have the circuit like this. So current is coming, and then we have a capacitor, and you can consider ESR also to be there. And then we have a load resistor. So the current that is coming is IL plus IL tilde. This is RC, this is C, this is R, this is plus minus V naught plus V naught tilde. So basically, if you now compare with the original circuit, so nothing has changed much. So everything remains same. Now instead of V naught, we have V naught plus V naught tilde because of the perturbation that we have considered, and here we have IL plus IL tilde. So now basically we are going to combine this with this. So now if you combine this and this, then the circuit will be filled. But if you see, our input is V in, but here we are getting D into V in plus V in tilde. So why is this happening? Because we are considering from this side of the circuit. So basically till now what we have done this side. So we basically consider this side of the converter. So we also need to consider this side. So that's why the input is not yet visible in the equations that we have done till now. So which variable will contain the dynamics of this? It is the input current. So now we are going to deal with the input current dynamics. So basically we need to cover all the dynamics of the converter. So we have inductor, we have capacitor, but this side is missing. So this is like this will come in the input current dynamics. So now we are going to consider the input current dynamics. So is this clear? If you have any doubts, you can ask.
Clear, sir.
Okay. So we can anyone tell me what is the expression for IE, IN?
Q into IL.
Yes, Q into IL. So now if we take the average sense, so we have I in over T is equals to average is D into IL over T. So now we'll do the perturbation. So we'll have I in plus I in perturb is equals to D plus D perturb IL plus IL perturb. Okay. So now input is I in plus I in perturb is equals to, we have IL plus IL perturb, right? So that term I would like to keep it as it is, because then we can write everything in terms of IL and IL perturb. So I will write it as D into IL plus IL perturb plus D perturb into IL plus D perturb into IL perturb. As I have mentioned, product of two perturbation can be considered zero because it is quite small compared to the other terms. So now we can also represent this in terms of a circuit. So my input current, then there is one branch, and then there is another branch. Okay. So my basically this is my input. So I can write it as V in plus V in perturb, and this is my I in. So I in plus I in perturb, and then we have D perturb IL, and we have D into IL plus IL perturb. So now if you see, similar to the inductor dynamics where we got an additional dependent voltage source, similarly in the input side we got an additional dependent current source. So now what we are going to do is we are going to combine all these three circuits. So let me just copy paste and then place them together so that we can understand what is going on. Okay. So now, if you look at this circuit, now what we can do is this entire thing can be replaced by a transformer. And then this can be connected. So now this will give the overall circuit of the buck converter. So now we are going to draw the overall circuit. I hope you are following.
Yes, sir.
So now let me draw the overall circuit. So we have the input. And then we had a dependent source. And then now it is represented by a transformer. So now this transformer has both AC and DC values. So it is represented uh, AC and DC. So this is the way people use to represent it. So, and we have one dependent voltage source. We have an inductor. We have an equivalent resistor. And then we have ESR of the capacitor and capacitor. And then output we have an resistor. Now let us write all the values. So this is V naught plus V naught tilde, and this is I in plus I in tilde. So this is D tilde IL, and it is 1 is to D, and this is D tilde V in, this is L, this is R equivalent. The current is IL plus IL tilde. This is RC, C, R plus minus. This is V naught plus V naught tilde. So now basically what has happened is here the current is D times of this current, and here the voltage is D times of this voltage. So which is what actually the transformer does. So the voltage on the secondary side will be D times the voltage of the primary side, which is V naught plus V naught into tilde. And the primary current will be D times the current in the secondary side, which is IL plus IL tilde. So primary current will be D into IL plus IL tilde. So this source I have put it here, and then the input side remains same. Oh, sorry. This is V in. This is V in, not V naught. This is V in. My bad. V in plus V in tilde. And then we have D tilde into V in, this expression, inductor and R equivalent. And output side we have VSR, capacitor and resistor. So is this part clear?
Yes, sir.
Yes, sir.
Yes. So basically now what we have done is we have considered a given circuit and we have considered the dynamics. So input current, inductor as well as capacitor dynamics. Then we have considered the average dynamics over a cycle. So little information is neglected. After that we have considered perturbation plus the average constant value. And then we have plugged these terms individually into the equation. And then we got a expression for each of these dynamics, which we have then represented in terms of a circuit, and then all these three circuits we have combined to get the overall circuit. So which is what exactly we are getting here. So this is the circuit averaging technique where we are averaging the circuit. So now if you go to the other method, which is quite similar, so I will show you how things are different here. So here it is the averaged switch model. So if you see in this circuit, all are linear, only the switching is non-linear, because inductor is linear, resistor is linear, capacitor is linear, all are linear. Only the switching is non-linear. So basically in the circuit averaging, what we are doing is we are basically linearizing these things. So instead of doing for the entire circuit, what we can do is we can linearize the circuit, this circuit itself. So what happens is we'll consider the switching and then we'll basically average the switch itself. So that's why it is called averaged switch model. So let us move to the other aspect, which is the averaged switch model. So just consider a simple circuit with switch and no on resistance. So this is our switching network. So this is say plus minus V in input side, and this is I in, this is S, and this is S1, and then this is say IL, and this is plus minus some voltage say V2. So now we need to get the relationship between V in IL and V2. So you can also consider the on resistance. So that also we can do. Maybe as we are considering the non-ideal case, let us also consider the same here. So we have resistance, switch, resistance, switch. So this is R on S, R on S bar. So now we need to write V2 in terms of V as well as this is my IN, right? IN terms of IL. So can anyone tell me what is the value of V2? What will be the value of V2?
V in minus I in into R on when switch is on.
Okay. And IN is equal to IL during that time. So we can directly write V in minus R on into IL. Else it will be minus R on into IL, right?
Sir, is it minus when switch is off, S bar will be on.
Huh. So
Okay,
it
okay.
is,
Understood.
yes. So it is like this one, right? Current is flowing from the bottom terminal. So when this is So when this switch is on, the current is flowing like this. So current flows from higher potential to lower potential. So bottom is ground. So V2 top terminal will be negative, lower potential. Clear?
Okay, sir, clear.
So now we can write V2 as same Q into V in minus R1 into IL. So the same thing what we have done previously, we are also going to do the same. So we have V2 plus V2 tilde is equals to Q will become D. So D plus D tilde into V in plus V in tilde minus R1 into IL plus IL plus IL tilde. Okay, so this is what we are getting. So now we can also further simplify it. So V2 plus V2 tilde is equals to D into V in plus V in tilde plus D tilde into V in minus R1 into IL plus IL tilde. Let this be our equation 1. Okay. So now what about I in expression? I in?
In is IL when S is on. It is
Okay.
0 when S is off.
Okay, yeah. So I in is Q into IL, right? Right, agreed?
Yes, sir.
So now I in is equals to, sorry, Q again will get average. So D plus D tilde into IL plus IL tilde. So now let us also simplify this. So we'll get In plus In tilde is equals to D into IL plus IL button plus D button into IL. And then we are of course neglecting the second order terms. So now we got two equations. Now what we are going to do is we are going to represent the same in terms of circuit. So let us consider the first expression, or let us create a gap. Yeah. So now we are going to do the same thing, circuit. So V2 is our output side and input side is dV. So the circuit can be written something like this. This is D into V in plus V in tilde, D tilde into V in. This is R on. This is IL plus IL tilde plus minus V2 plus V2 tilde. Agree? Everyone agree how we are getting this? I have just represented it. Two voltage sources, one R1 resistance and one voltage source, one voltage at the output.
Okay, sir.
Now we are going to do the same for this. So input is In plus In tilde. And then we have one voltage source, a current source here, and we have another current source here. So this is plus minus V plus V tilde. This is IN plus IN tilde. This is D tilde into IN. This is D into IN. IN tilde. Clear? Just represented the circuit. Now I have a question for you. In the case of previous circuit, we got R equivalent, which is R on plus RL. But here we are only getting R on. So can anyone tell me why is this so?
Because we have considered only the switch in the second case.
Yes, very good. So basically, in the first case, we have considered the dynamics of the inductor and then we have gotten the overall circuit. Whereas in the case of second case, we are only considering this blue part actually. So what we'll do is we'll consider the blue part and then we'll attach it with the green part. So that is what we are going to do in the second part. So now, so let us redraw this both the circuits together. So let me copy this part. This is at the output side. This is at the input side. So now we are basically doing the switch model. Okay, so now if we draw the model of the switch, we will get something like this. So there is less than a minute. If this meeting ends, kindly join back so then we can continue the discussion. So this is our V in plus V in tilde, and this is our I in plus I in tilde, D tilde I in AC plus DC, and here we have I in plus I in tilde, D tilde R out plus minus V2 plus V2 tilde. Is this clear until this point? This is the switch averaging. Is this clear till this point? If this meeting ends, kindly join me. Any doubts?
No, sir, it's clear.
So now basically what I'm going to do now is, this is the switch model, right? So we found the averaged model of the switch. Now what we are going to do is, we are going to connect the output, whatever is there. So what is there? We have a RL, we have a inductor, we have ESR, we have capacitor, and then we have resistor. So this is RL, this is L, this is RC, C, R, and this becomes plus or minus V0 plus V0 tilde. And if we combine this is what we call R equivalent. So now if you combine the circuit that we got over here and this, so basically methods are different, but the result is the same. And this ratio is 1:D. So basically, in the first case, the approach is slightly different. We have averaged the dynamics of the inductor, capacitor, and input. We have not considered the switch because switch is actually governing the dynamics of the these inductor, capacitor, as well as input current. Whereas in the case of second case, we have not touched inductor or capacitor. We have replaced the switch with its averaged model, and then we have combined the output side of the buck directly, and we are basically getting the same expression. In the case of state space averaging, we'll get the state space and then we'll apply averaging on the state space, but then you will not get any such model out of it. Instead, you will get the state space representation only, like v naught tilde equal to c into x tilde. So you will not be able to visualize anything, but you'll get everything in terms of matrices, which is very easy for computing if the matrix size increases. Whereas in this case, if the dynamic elements increases, then it will become very difficult to analyze them sometimes in terms of the circuit. But if we can, then it is very beneficial so that we can see which term is caused by what term. So if you see here, I can see that I'm getting an additional voltage source because of d tilde. Similarly, and it is dependent on input voltage. Similarly, I am getting an additional current source in terms of d tilde, and it is also dependent on IL. So we can get some understanding. So now I can see that, okay, if the perturbation is more, then the current will be more. Or if my Vin is more, then the voltage across this is more. So we can get some idea about which is affecting what. So in this way, we can get the model. Although I have shown for buck, I can similarly do for boost as well as buck boost. So the methodology remains the same, and the final objective is to get such circuit. So any queries? If no, then we can start and solve few problems. Any doubts?
No, sir, it's clear.
So now I have asked draw the a DC equivalent model. So can anyone tell me if you know what is a DC equivalent model? So basically this is the overall model which consists of DC plus AC quantities. So when I say DC model, so what is a DC equivalent model?
Frequency independent parts, that's the
Yes,
DC.
yes. Very good. So now, whatever he has said is absolutely correct. This has both constant terms as well as frequency dependent terms. So if we consider only frequency dependent terms, it is called AC equivalent model. If we consider only non-frequency dependent terms, then it is called DC equivalent model. So now, let us. So how are they like matter? Why DC equivalent model is needed? Why AC equivalent model is needed? So DC equivalent model uh, will be used so that we can get the DC operating point details. So we can get the steady state DC operating point, or we can get the details of IL VC at steady state, basically steady state. And how is AC equivalent model? How is AC equivalent model used, and what is the benefit of this, or like how it is being used? So using this, we can get something called small signal transfer functions. So this can be used to design the controller. And that's why modeling is very important, because we need to, the final objective is to implement the designed controller in hardware or simulation anywhere. So for designing the controller, we need a model. So how to get the model? So that is what we are studying in this week. So once we get the model, then we'll use this model and then we'll design the controller. So this is there in the next week. So this is in week 6. And I think in the subsequent weeks, we'll get the controller design and then overall how to make the simulation and check the response. So these are in the subsequent weeks. But in this week, we are getting the overall model and DC equivalent model. So now DC equivalent model means, so which terms will be gone? This is gone. We're going to use a different contrasting color. So this is gone. This is gone. D part of IL will be there or no? D part of IL
Removed.
removed. So this is also not there. And this is there. D part of BN
0. Short circuit.
0. Yes. And IL part time is also not there. And V naught part time is also there. Not there. Also, it's a DC equivalent, right? So DC means steady state has reached. So what happens to the inductor and what happens to the capacitor?
Inductor short circuits, capacitor open circuits.
Yes, so inductor is short, capacitor is open. So capacitor I will remove. So if the capacitor is removed, there is no meaning of RC because there is no power. But I'll just write it in the circuit. So we have a V in here, I in, and the transformer. So we have V in, I in, and the transformer. And then here I have R equivalent, inductance is shorted, capacitor is open, and I have a resistor. So this is V in, I in, 1 is to B, R equivalent, RC, R plus minus V naught. So now I can get, and the one important thing, so because it is DC, now we'll not write that AC type. So this is like a DC transformer. And one most important thing that I have forgotten is the dot convention. So these are the dot convention because that decides the polarity of the voltage as well as the direction of the current. So I'll mention it everywhere. Here also. So this is the overall DC equivalent circuit. Clear?
Yes, sir.
Okay. So now using this DC equivalent circuit, now we can calculate whatever I have asked in the next question. So, hmm. So I have asked what is the voltage gain and efficiency expression. So first let us, in order to compare, so this is for non-ideal buck, right? For ideal buck, what is the voltage gain expression? If I am calling it as kV, and what will be the efficiency? What is kV for buck?
V naught by Vn.
V naught by
D.
Vn, also Vn, yes. So V naught by Vn and D. And efficiency?
Same.
Efficiency is what? Efficiency is V naught into I naught by Vn into In, right?
Oh, yes, yes.
So V0 is what? dVin. And what is In? D into I naught, right? So efficiency is 1 because there is no loss element. So I'll get efficiency to be 1, or if I want to say in percentage, 100%. Okay. So now I'm giving you task. This is for ideal buck and this is for non-ideal buck. So can you calculate the expression of kV for non-ideal buck? So I'll give you maybe 5 minutes time. So you can calculate in the meantime and then we can cross check. Are you doing? You are doing right, all of you. Arun, Navin, and Rahul.
Yes.
Okay, okay,
Sir, voltage gain is it D into R by R equivalent plus R.
okay. So let me write the answers that you are getting. Then I'll solve to cross check. So what is the kV that you are getting?
D into capital R by R equivalent plus capital R.
Okay. What about others? Are you getting a similar expression or something different?
Not yet reached. Give a
Okay,
couple
okay.
of.
Okay, okay. I'll give you time. Take your time.
Yes, sir. This expression.
Okay, okay. So efficiency has anyone calculated? So will you please also calculate efficiency. So once all of you solve, I think only two people have solved. Someone is yet to tell whether KV is matching or not. So you take your time. Once you solve, then we can cross check. I'll start solving. So efficiency has anyone solved?
R by R equivalent plus R.
Okay. Okay. So now let me check whether it is coming to be correct or wrong. So now I want to bring this V in onto the other side. So it will be dV in R equivalent and R. So we have this expression R equivalent R. So this is dV in can you see my screen?
Yes, sir. Yes.
Yes.
So plus minus V naught. So now we can get V naught is nothing but R by R plus R equivalent into dV in, and we know Kb is nothing but V naught by V in. So it is D into R by R plus R equivalent. So now if I further simplify, I can get Kb is equals to D into 1 by 1 plus R equivalent by R. Also I can write as Kb is nothing but D into 1 plus R equivalent by R inverse. So now if you see, if there is no R equivalent if it is 0, then Kv is D. So, so what is happening? Because of the uh, parasitic, I will say parasitic, which refers to R equivalent. So whether my output is lesser than expected or more than expected, like more than ideal case. So I non-ideal case, whether the for the same duty ratio, everything input voltage, if I have small R equivalent, whether my output voltage is more than the ideal case or less than the ideal case.
Sir,
Less
sorry to
than that.
interrupt. I
Yes.
I don't think what you have written is reflecting on the screen, or maybe my internet issue.
Okay. Can others screen see or
Same problem is here, sir. We
okay,
can see
okay,
the screen, but whatever you're writing is not reflecting.
okay, okay. Let me reshare it. Can you see or still some issue? Have you seen
Yeah, now it's
KV?
reflecting.
Okay, okay, yeah,
Yes.
okay, okay. So my question is, so the KV expression is D into 1 plus R equivalent by R into whole inverse. So now I am considering two cases. One is the ideal case with given V in, given duty ratio, given load resistance, and non-ideal case with all the parameters same and some finite R equivalent. So on the left hand side, ideal case, I got some V naught. And in the right hand side, say non-ideal case, I have V naught 2. So V naught non-ideal. So what will be the relationship between V naught non-ideal and V naught ideal? Which is more, which is less?
V not ideal will be more.
Yes. So in the case of non-ideal case, there will be a voltage drop. So like this is the case, right? So this is for non-ideal, whereas in the case of ideal, this R equivalent is not there. So it is basically shorted. So V naught is dV in. But because of this R equivalent, there is a drop across this. So because of this drop, my V naught will be slightly lesser than D depending upon the value of R and R equivalent. If R is much higher than R equivalent, then V naught tends to deviate slightly smaller. Only when R equivalent is 0, then we have V naught equals to dV. So ideal case, non-ideal case. So in the case of ideal case, we have Kv is equal to, I will get it for Kv equal to D. And in the case of non-ideal case, I have Kv equal to D into 1 plus R equivalent by X. Fine. Now let us go to efficiency. So efficiency, is V naught into I naught by V in into I in. So V naught is KV into V in, and I naught is I naught. V in is V in, I in is D into I naught. So if you cancel V in, I naught, V in. So efficiency is KV by D. So what is my efficiency then? 1 plus R equivalent by R inverse, right? Agree, everyone? How we are getting the efficiency expression? So whoever has told this expression, it is right. Hello.
Yes, sir. It
Okay.
makes sense.
So if you have any queries, you can ask, else we can move to the next problem. Okay. So here I have given another such example, and it is related to the previous problem. So you can use those formula and then you can try this problem. So once you tried it, then we can discuss the solution. So I'm giving you another 5 minutes. So all of you please solve. And then once you solve, then we can cross check the answers and then I will start solving. So did you understand the question or should I explain?
It's understandable, sir.
Okay, okay. Someone has mentioned, Arun has mentioned D is 0.0834, and Navin also mentioning D is 0.0836. Arun has mentioned B is 0.08, and ideal case 100%, non-ideal case 95.97%. Okay, let us wait for others, and then once everyone uh, gave it a try, then I'll start explaining.
I'm getting A as 0.07677. Maybe I made some mistake.
Okay. So now that everyone has tried, let me just solve A part at least. So the duty ratio to achieve an output voltage of 0.8. So we know the relation. So this is the relation. We know V naught, we know V in. We have to calculate the duty ratio. So let us use this and then let us solve. Okay. So this is the A part. So now kV is V naught by V in 10, which is D into R is 0.05, and then R equivalent is 2 milli plus 1 milli, 2.1 milli. So it is 0.05 plus 2.1 milli. So this is 0.08 into 1 plus 2.1 milli by 0.05, which is 50 milli basically, is equals to D. So my duty ratio D is 0.08 into 1 plus, if I multiply by 1000 on the numerator and denominator, I will get 1 plus 2.1 by 50. So let me calculate. Okay, I don't have my calculator with me, so uh, we have 0.08 bracket. Let me calculate 2.1 by 50. 2.1 divided by 50 is 0.042 plus 1 into 0.08. So I'm getting 0.08 636. I think that's what everyone was telling. 0.08336. So 0.084. So the duty ratio that I'm getting is 0.084 approximately. So I hope it is clear now. Rahul.
I did the same thing, but somehow, okay, I'm using the NPTEL calculator, maybe some.
Okay. Because it should be greater than 0.08, because ideally it is 0.08. So it has to be slightly more than that to achieve the same voltage, because there is a drop across this equivalent resistance.
Hmm. Okay.
Okay. So now A is done. Now B part is, what is the duty ratio for ideal case? So ideal case, it is simpler. KV is nothing but V naught by V in which is equals to duty ratio. So it is D is 0.08. Okay. Now, if we move to the case C, we have efficiency. So in the case of ideal case, we know it is 100%. In the case of non-ideal case, we know it is 100 into 1 plus R equivalent by R inverse. So it is 100 into 1 plus 2.1 by 50 inverse. So I hope everyone is getting the same answer. So I will not calculate. I think 95.97. That's what people are telling. So in this case, it is 95.97%. So is this question clear for everyone?
Yes.
Okay. So if you have any queries, you can ask, else we can proceed. And as we have time, I think I'll cover the state space averaging as well. Is that fine? Or if you have any queries, you can ask, else I'll move to state space averaging and I'll quickly summarize that technique as well. Okay. So I guess.
No queries, sir.
Okay. So now let us move to state space averaging. So for state space averaging, first we need to get the state space model. So let us. State space averaging. So I'll consider the same buck converter, non-ideal. And then we have to draw the state space. So whatever we already have, I'll take those so that it makes our life simpler. So state space averaging, we have the VL. So I'll consider this. So an equivalent is there. And C is also there. So let us ignore ESR part for this case because ESR makes our life very, very difficult. So I'm skipping the ESR part. So let us ignore the ESR as of now. In the state space average, it becomes much easier to explain because only the matrices change. So like everything remains same. So only the matrix changes. So you can write a code for everything. And if something is added, you can only change the matrix and everything remains same. Whereas in the other case, some terms needs to be added or removed. So both are more or less same. But here it is just the matrix that will be changed and everything remains same. There some equations will change slightly. So this is the expression that we got for the inductor dynamics as well as the capacitor dynamics. So now if we consider our states to be, so how many states are there in this circuit? See if I'm considering X, how many states are there?
2.
2. So we'll consider IL and VC, which are like our X1 and X2. Two energy storing elements. So two states. And also this meeting will end in 1 minute. So if this meeting ends, kindly join back. Then we'll be in the last 40 minutes. So now I will write my X1 dot is IL dot. So from my first equation, I can get it as Q into V in by L, Q into V in by L minus R equivalent into IL by L minus V0 by L. So now if I write in terms of X1 dot, I can get X1 dot equal to minus, basically this is V0, so minus R equivalent by L into X1 minus 1 by L into X2 plus Q by L into Vn. Vn is my input. So Vn is basically U. So is this expression? So this is my equation 1. Okay. Now I can get a similar equation for the second case, which is dv naught by dt. So x2 dot is nothing but il minus v naught by r. So if I use a different color, then I'll have x2 dot is equals to v naught dot is equals to il by c minus v naught by rc. So now if we write this, we'll get x2 dot is equals to 1 by c into x1 minus 1 by rc into x2, right? Is this clear? So because it is state space averaging, so we need to get state space first. So once we get the state space, then we'll do the averaging to the state space. In the first method, circuit averaging, we are doing the averaging to the circuit directly. In the second method, it is averaged switch model where we are averaging the switch. Now it is state space averaging, so we'll apply averaging to the state space. So is this clear until this point?
Yes, it is.
So now what I'm going to do, I'll write the entire state space. So we have x1 dot x2 dot. So the first term will be minus r equivalent by L. Second term is minus 1 by L. This is 1 by C. This is minus 1 by RC. Into x1, x2 plus Q by L 0 into V. Similarly, if my output is V naught, so then I can write my V naught is a matrix C into X, and X is IL and V naught, right? So we'll have 0, 1. Maybe it's a different color. 0 and 1. X1, x2. Clear?
Yes.
So now basically there are two types of modes. So when we do state space averaging, so this is the overall state space that we have obtained. Now let us write a generic expression of state space. So we'll have x dot equal to ax plus bv in, and y is equals to cx. So usually we have again two types of modes can be. One is during on time and one is during off time. So we'll do the exact thing what we have done in the circuit. So first we'll do the averaging for a certain period Ts is equals to average of A into average of X plus average of B into average of V in, then average of Y is equals to average of C and average of X. So can anyone tell me what do I mean by average of the matrix A? Like what is the average of a matrix?
Like sum of the elements divided by 2.
Okay, that is one way to put it. Anyone else? Okay.
The matrix during turn on, if it is A1, and during off condition if it is A2, then we have to multiply by that duty ratio.
Yes, yes, very good. So if we see not all the matrices are same during DTS and 1 minus DTS. For example, if we consider this expression, so this is B. So now I can call it as B1. I can call it as B1, which is 1 by L and 0. And I can call it as B2. which is 0 and 0. So now the average of the average of B will become D into B1 plus 1 minus D into B2. So that is what we are going to do now. So our A1 is equals to A2. B1 is not equal to B2. Similarly, C1 is equals to C2. So A1 equal to A2 means average of A is equal to A only. And the average of B will be D into B1 plus 1 minus D into B2. Similarly, average of C will be C itself. Clear? Any doubts? Okay. So if no, then what we did previously, we have put steady state plus some perturbation, right? So same thing, exact same thing we are going to do now. So if you consider the first expression, so x dot is what? Derivative. So if I consider x to be some x steady state plus x tilde, now the derivative of this will be x steady state dot plus x tilde dot. X steady state is a constant value, so it will become 0. So we'll get x tilde dot. So now if we directly write that x tilde dot is equals to A matrix is A only. So A into now x is x steady state plus x tilde. And now coming to B, B has two terms. One are D into B. So now it becomes D plus D tilde into B1 plus 1 minus D minus D tilde into B2. This entire thing into V in plus V in tilde. Clear, everyone?
Yes, sir.
Okay. So now what I'm going to do is, first of all, I will simplify this. So kindly pay attention. So first I'll segregate the steady state terms dB1 plus 1 minus D into B2. So this is one term, and then D tilde into B1 minus B2. So this I can write, right? Did I miss any term? So I have segregated the constant terms, and I have segregated the D perturb terms. Any doubts? Okay. If no, then I'll proceed. So the other term is V in plus V in tilde. And everything remains same. So now if we go to the next step, so now what I'm going to do is I'll just rewrite the entire expression. So x tilde dot is equal to A into x steady state plus A into x tilde plus dB1 D into B1 plus 1 minus D into B2 plus, sorry, this entire term into V is one term. Then we have D tilde into B1 minus B2 into V. This is one term. And then we have another two terms, which are D into B1 plus 1 minus D into B2 whole into V in tilde plus D tilde B1 minus B2 into V in tilde. So this is a product of two perturbations. So again, this we are going to ignore. Now, if we actually write x tilde dot, so this is basically x steady state dot plus x tilde dot is equals to, and we know that this value is 0. So this is corresponding to the DC. So now if we are going to proceed further, we need to first understand one important aspect, which is, let me go back. So in the original circuit that we have over here, so this is the overall module, like overall model, which consists of the AC plus DC. And then we know that we can segregate the DC separate and we can segregate the AC separate. Same thing here. This entire thing, so this entire thing is DC on the RHS side. Similarly, this is the DC on the LHS side. So we can actually write like this. So we can get the DC part. So the DC part gives us x steady state tilde, which is 0, is equal to, again, sorry, my bad. This x tilde is not there. So this is again AC. So this is belonging to AC. So the rest of the parts, which is A into x steady state plus D into B1 plus 1 minus D into B2 into VE. So now if you see, basically B2 is 0, right? So if we substitute, B2 is 0, so this will be D into B1 only. Agree, everyone? B2 is basically 0. So I'm substituting. Till now I have not substituted, but now I'm going to calculate the values. So that's why I have substituted. Is this simplification clear for everyone?
Yes, sir. So is it valid only for buck?
Yes,
Right?
it is
B2
valid
is
for
0.
buck. Yes, it is only valid for buck. So all these are only valid for buck, because in the case of boost, A1 and A2 may not be same. B1, B2 are same, and C1, C2 may not be same. So there, the expression will increase because we didn't have A1, A2. This simply became A. Whereas if you have A1 and A2, then again we'll get similar terms. How we are getting for this, we'll get same here. Like A1, D into A1 plus 1 minus D into A2 plus D perturb into A1 minus A2 whole into x steady state plus x perturb. So we'll get 4 terms, out of which only one term will be 0. So we'll have 3 terms. But now A is A, we have only 2 terms. Else we'll get one more additional term. So all this I'm doing for buck. So like Kelvin will be doing tomorrow for boost, so that there will not be any confusion. Today everything buck, and the same thing tomorrow it will be boost. So now,
Okay, sir.
if we bring everything onto one side, Ax steady state equal to minus D B1 into VE. So now I can get my x steady state is equals to minus A inverse B1 D into VP. So this is how we can get the DC operating point. So in this case, this is the DC operating point. So now if you see, we cannot actually analyze anything from this expression until we put back the matrices, and then if we calculate, then we can get the expression. So basically, if you see the previous method, here we could get a actual intuition based, or we can actually feel what is happening, that if there is any parasitic, then the output voltage is slightly lesser than expected, and you can actually see it, and you can also actually understand why it is happening and which term is actually responsible for that. But whereas in this method we got a mathematical equation. Now you need to plug in A inverse. So now you have to put A inverse, so you have to do the inverse of this and then multiply by B1, which is this B1 matrix, and then you have to, you can get x steady state, which IL steady state, V naught steady state. So from there you can get the V naught steady state, which will exactly match with what we have obtained over here. But in this method, you can actually see what is happening. Whereas in this method, you will not be able to see. It is in terms of matrices, although it becomes, or it feels more generic, because I can do the same for any converter and I can get the expression. All I have to do is put A, B, C, D, like, and V in, and then I can get. So this is more generic. I only need to change the matrices. Whereas the previous case, it is like specific because the circuit will change from converter to converter. But there you can actually feel and see what is happening, which is responsible for what. Here it is not like so intuitive. Here it is more mathematical. So now that this term is gone and these terms are gone, now let us segregate the other terms. So x tilde dot. So x tilde dot is nothing but ax tilde dot a into x tilde dot plus this we already know, db1 is db1 only. So this entire expression is db1 into v in tilde plus b1 minus b2 into v in into d tilde. So we got such expression where we have x tilde, v in tilde as well as d tilde. So this is the expression that we got. Similarly, if you do y equals to c into x, right? So y tilde is what? Like now y is what? V naught. So v naught plus v naught tilde. C is c only, right? Because average of c is c and average of x is x steady state plus x tilde. So this is one expression that we have obtained. So this is for the states IL and V naught dot. So this is the regarding the states. Now, if you go for the output, we know y equal to cx, right? Y equal to cx average. So now if you substitute what is y? V naught plus V naught tilde. So V naught plus V naught tilde equal to c is c only and x is x steady state plus x tilde. So now if you segregate, we'll get V naught plus V naught tilde equal to c into x steady state plus c into x tilde. So again, I can segregate DC DC and AC AC. So I'll get first expression is V naught is equals to c into x steady state again. This is DC operating point. And if we get the other expression, the rest of it is the AC V naught tilde equal to c into x tilde. Okay, this will be our equation 2. So model may be anything, but our final objective is to get that small signal transfer functions. And then using the small signal transfer functions, I want to design the controller. So there are various methods which I can use to reach the same destination. The path is different and the difficulty is different. So depending upon our comfort and which suits our application or which suits our demands, then we go by that method. So some people are more comfortable with state space averaging. Some are more comfortable with circuit averaging. Some are more comfortable with average switch model. So my personal preference is circuit averaging because I feel it is more comfortable for me. But if you feel state space averaging is more comfortable for you, then you are free to choose any methods because all methods lead you to the same destination. So different methods, but the objective is same, and also the methodology that we have followed is same. So first we have obtained the equations in all the three cases. Then we have did the averaging, neglecting the ripple. Once we did the averaging, we have considered the steady state term plus some perturbation, and then we have neglected the higher order terms, which is the product of two perturbed terms. We have ignored it because it is small, and then we have simplified it. And in all the three cases, we got a final expression which consists of DC plus AC, which we can segregate. So we can segregate DC terms and we'll get one expression using which we'll get DC operating point. and using the AC perturb terms, then we'll get another set of equations using which in the next week we are going to design the small signal transfer functions, using which in the upcoming weeks we'll be designing the controller and then implementing the simulation. So this is the overall idea of how the modeling and different analysis are required in switch mode power converters and how we can use them to design the controller by deriving the small signal transfer. So this is the overall idea of this week's discussion. So if you have any doubts, you can ask. Else I'll summarize what we have discussed in week 5. So any doubts? Are all the methods clear? If you have any doubts regarding this week or any week or anything regarding assignment, you can ask. So this week is quite simple. Only you need to know the process and then you should not make any mistakes. So practice as much as possible. Whatever sir has covered in the lecture, you solve and derive the models for all the converters that sir has already discussed in the lectures. Then it will be easy for you to do in the assignment. So this week is simple and straightforward. So that's why we have completed quickly. And I guess you have also understood and enjoyed.
Yeah, in the assignment, that answers which you have to fill up, like
Yes, yes.
negative values are also accepted, right? Like I
Yes,
can
yes.
give, like if I'm getting the answer as minus, I can give minus
Yes, you should,
something
you should,
point.
you should.
Up to. Okay.
So if sometimes in the question they will ask what is the absolute value. Like if you see non-inverting buck boost output is positive, but in the case of buck boost output is negative. So the question can be written as what is the absolute value of the output voltage. So there you will have to enter cost value. But sometimes some coefficients are negative, say A1, A2. Here also, if you see in the above matrix, so my matrix except one term all are coming negative. So if I ask you what is this value, so it is minus R equivalent by L. So it is same some minus 5 into 10 to the power minus 6. So they will give what is A2 or A2 equal to dash into 10 to the power minus 6. So I have to write minus 5. Sometimes they will give A2 equal to dash into minus 10 to the power 6, then you have to enter 5. So it can be twisted here and there just to check whether you are paying attention or whether you are attentive or not. But answers can be negative as well as positive. And sometimes they'll also ask you to enter integer, say duty ratio you are getting 0.63. So they'll say answer enter up to 2-digit decimal. So you have to write 0.63. Say sometimes you got 0.79 and they will say enter up to 1 decimal point. So you have to write 0.8. So you have to approximate it. And in such cases, they will always give range. Say your duty ratio is 0.63. They can give range from 0.61 to 66. So sometimes we consider up to 3 decimals, sometimes we consider up to 2 decimals. So some people might have gotten 0.62, but some people might have gotten 0.63, some people might have gotten 0.64. So considering all these things, they'll give a range. So even if you skip few decimals here and there, you'll end up close to the value, and that range will ensure that you will get the marks. So this is the overall idea of range. Say there is a question where they will ask input voltage is 5 volt, buck converter output voltage is 2.5 volt. So the duty ratio is half, 0.5, very straightforward. So their range is not needed. So range does not like make sense there because it is very straightforward and duty ratio is 0.5. So in that case, maybe range is not given, but majority of the cases, 95% range will be given. So no need to worry.
And sir, one more thing.
Yes.
In a question, if it is I'm getting the answer as recurring, okay, and I'm asked to give up to 2 decimal places, like I'm
Okay.
getting the answer as 0.86666. So
7.
should the answer be 0.87 should be
Yes,
the answer, right?
0.87.
Or
Yes.
should
0.86 also is fine. So say the point answer is 0.867. Considering 0.86, considering 0.87, the range can be given as 0.85 to 0.90. So it will ensure like a range so that all the possible answers will fall in the range. So both will be given correct.
okay? Thank you.
Okay. So if you don't have any further queries, then I'll quickly summarize and then we can end this session. So in this week 5, we have discussed about different approaches to get the overall AC equivalent or DC equivalent or both. So in the beginning, we have discussed about two methods. One is the circuit averaging and the second one is the average switch model. Towards the end, we have discussed about the state space averaging. In the case of circuit averaging method, we'll consider the circuit in an average sense, we'll neglect the ripple and we'll consider the average in a switching cycle. So in this case, what you have to do is you have to write down the equations for inductor, capacitor, and any other, in the case of buck converter, input current, so that we'll capture the input dynamics as well. So once we write the inductor dynamics or capacitor dynamics or whatever, then we have to consider it in terms of an average sense. Once we consider the average sense, we'll consider the DC value plus the AC perturbed value, and then we substitute back these expressions in the above expression, whatever we have obtained. And then we'll ignore the higher order terms, which is product of two perturbed terms, because it will be very small. So this is another approximation that we consider. So once we get the expression, we represent this expression in terms of a circuit. Similarly, we'll do for the capacitor. Similarly, we'll do for the input, and whatever circuits that we have obtained, we'll combine all these circuits into a single equation, which will give us the overall circuit, which consists of both DC as well as AC. So now if we consider all the DC terms, it is a DC equivalent model. If we consider all the AC terms, it's an AC equivalent model. But this consists of both AC as well as DC. So this consists of both the information, but usually we will not need both. We'll be needing either DC operating point, so we'll use DC equivalent model, or small signal transfer function, so we'll use AC equivalent model. Next, we moved on to another method, which is the average switch model, where we have considered only the switch and we have applied the averaging to the switch. So input output voltage relation, input output current relation, two equations, and then we have applied the averaging, and then we got the equivalent circuit for both these two expressions, and then we have combined both of these, and then we have obtained the average switch model. So now this is not the overall model of the circuit, but the average model of the switch. So now we need to combine whatever is the circuit that is left and not considered in the average switch model. Here output side is not considered, so we have combined this, and then we'll get the same equivalent circuit model that we have obtained using the first method, which is the circuit averaging. So here we have discussed two different methods, and we have seen using both the methods, we have gotten the same circuit model, same overall model, and we should be getting. So now we have discussed about the DC equivalent model, where we'll consider the DC operating point, and we have considered all the DC quantities, and from this we can get the voltage gain as well as the efficiency. So we have considered an ideal buck converter as well as a non-ideal buck converter, and we have derived the voltage gain as well as the efficiency. And then we have seen what is causing the difference in the ideal and non-ideal efficiency as well as voltage gains, and in which scenario will these two terms become equal, and why the output voltage will be lesser in the case of non-ideal, and we have also seen that which term is causing that. So we'll get an intuitive understanding that okay, there is a drop across the parasitic, so output voltage will be of course lesser than what is expected, because some voltage is dropped, and if the parasitic is 0, then both will converge to the same value, which is D. Similarly, efficiency is 100% if there is no parasitic, but it will be lesser than 100% if there is parasitic, and again it depends upon the load current as well. So if the resistance is very high, then the efficiency will be close to 100%, and if the load resistance is small, then it will be poor, because the drop across R equivalent will come closer to R. Now we have solved another problem where we have given the values and we have seen mathematically, so that we can get a number and we can see how lesser it is than 100%, or how much will be the difference in the duty ratio to achieve the same voltage in the case of ideal case as well as in the case of non-ideal case. Then as time permitted, we have also discussed about the state space averaging, where we have to first build the state space model, and then we have to see which matrices are changing with respect to Q and which are not. And then we have to first find the averaged matrices value. And then again, same thing, we have applied the averaging to the state space. And once this is done, we have considered the steady state term plus the perturbed term. And then all the steady state term will lead to the DC operating point. All the perturbed terms will lead to the AC equivalent model. Similarly, output equation, we have again obtained two equation. One is for the DC operating point and one is for the AC equivalent model. So with this, we'll complete week 5. If you have any queries, we can discuss, else I'll wind this session here. Any queries you have?
Sir,
Yes,
one
yes.
doubt regarding Not related to this. In the
Okay.
first week, you have shown that DigiKey website and how to select
Yes,
components.
yes.
So suppose I have purchased some components. In the
Okay.
next step, to build a simple boost converter, I don't have any previous experience in PCB design.
Okay.
So can you share some resources
Yes.
to do?
Yes. So there is this guy, Robert Fahrenheit. So I'm sending in the chat. So you can subscribe to this guy's channel. He's, I think, like quite famous in PCB design. So there is one Altium lecture at the beginning. So you search Altium. So Altium is a software. It's a PCB design software. So you can search Altium tutorial, and you can subscribe to his channel. So there are a couple of videos that he has, like in which he has demonstrated about the layout. So you can go through this. Also, you can find some other reference materials, but these are what I have followed, and they are quite good. This guy is very professional in terms of Altium design. So he explains in detail, and they are good. So you can subscribe to his channel and then follow the tutorials. Also, you might find some other reference material which may be like better. So in that case, you can follow those videos as well. So did you get the two messages that I have sent in the chat box?
Yes, sir, I received.
Okay.
So if we use some somewhere I have seen that in some Hilem sheet, if you insert discrete components and terminals, will that work similar to PCB, or will there be
Which one? Which one?
in a Hilem sheet, if you
In
make
a high.
holes and Hilem, HYLEM, Hilem sheet,
Okay,
like
okay.
that.
I'm not aware of that.
Uh, okay.
Okay, this is regarding layout or something.
Not layout, actual hardware, but if we are not familiar with PCB, somewhere I have seen like inserting terminals in this wooden board like setup.
Okay, okay, okay. I'm not aware of that, so I cannot comment on that.
Okay, so PCB will be better.
Yes, yes, PCB is always better, but again, it like takes some time to learn and then make and then send it for fabrication and test. But it's a very nice exposure that you will get. You will learn many things.
Okay, sir. Okay, thank you.
Also, you can use spice simulations like LT Spice or other Spice, Tina for TI, P Spice for TI, Cadence, Simplest softwares. Some are paid, some are free, where you can use actual switches, and then again you can run the simulation. So it will be more realistic than what we are doing in the MATLAB, where we are making custom model. But in the case of Spice, we'll use the actual switch. So all the losses, everything, parasitic, everything are already incorporated in the Spice model. So it will be more realistic. But again, these are not covered in this course, and they are like outside the syllabus of this course. But people are always welcome to explore different software so that their simulations will be more realistic.
Okay, sir. Thank you.
So if you don't have any more queries, then I'll end this session here. I will wish you all the best for week 5. See you again in the next week with week 6 continue. Okay, then good night, and I wish you all the best.
Thank you, sir. Good night.
Thank you. Good night.